Hi, my name is Brian Caffo, and this is Mathematical Biostatistics Bootcamp, Lecture 9 on confidence intervals. In this lecture, we're going to talk about confidence intervals, mostly in the setting where we're going to assume that our data come from a Gaussian distribution. So we'll talk about confidence intervals for variance. We'll talk about Gosset's t-distribution, and we'll use Gosset's t-distribution to create confidence intervals for means. And we'll touch on the subject of profile likelihoods. In the last lecture, we talked a little bit about the central limit theorem, and we talked about using the central limit theorem to create a confidence interval. I think in that example, we created a confidence interval for a binomial proportion. Now we'll discuss the creation of better confidence intervals for small samples using Gosset's t-distribution, small samples where we're willing to treat the data as if it's continuous. So to get to that point, and Gosset's t-distribution is often called student's t-distribution, and we'll explain why in a little bit. So to discuss the t-distribution, we first have to go through what the chi-squared distribution is, and so we'll develop that first. And at any rate, what you'll probably hopefully have noticed whenever we create confidence intervals, there seems to be some kind of prevailing logic that we use. Basically, we try to create a probability statement, and then we, in a sense, manipulate that probability statement to generate an interval. Well, this strategy is codified here. So basically, we create a pivot or a statistic that doesn't depend on the parameter of interest. I should say we create a pivot or a statistic whose distribution doesn't depend on the parameter of interest. So, for example, if you use the central limit theorem, if you take a sample mean, subtract off the population mean that you're interested in, and divide by the standard error, well, that statistic clearly depends on the parameter of interest, but the distribution of that statistic, at least in the limit, doesn't depend on the parameter that you're interested in, the sample mean. And then after we've created that pivot, we solve the probability that the pivot lies between bounds for the parameter. And so that's the kind of general strategy we'll go through. You don't have to really know or really understand this strategy at a very general level, but just in case you're wondering, why does it always seem like we're generating confidence intervals using basically exactly the same technique? It's because we're employing a strategy kind of like this. So let's talk about the chi-squared distribution. So remember that S squared is the notation we've been using for the sample variance. And let's further assume that the data that comprise the sample variance are all IID, normal with mean mu and variance sigma squared. Well, then n-1 times the sample variance divided by sigma squared is a random variable that we call a chi-squared distribution, and the chi-squared distribution has an index, something that differentiates between different kinds of chi-squared distribution, and we call that index the degrees of freedom. So this statement right here will be read: the normalized sample variance follows a chi-squared distribution with n-1 degrees of freedom. So the chi-squared distribution is a skewed distribution, and it, of course, since the sample variance has to be positive, it has support between 0 and infinity. And the mean of the chi-squared distribution is its degrees of freedom. And we can see that very directly because we recall the sample variance is an unbiased estimator. That's why we divide by n-1 instead of n. So if you look at this equation, when you take the expected value of s squared is sigma squared, you can see that expected value of n-1 s squared divided by sigma squared, the sigma squareds would cancel out and you'll get that degrees of freedom are its expected value. The variance of the chi-squared, by the way, is twice the degrees of freedom. As an aside, we're not actually going to spend a lot of time doing this, but as an aside, you can use this idea to create a confidence interval for the variance. So imagine if I were to draw a chi-squared density, and chi-squared n-1 alpha is the alpha quantile from that distribution. Then imagine taking the, say, alpha over 2, let's take alpha to be 0.05, for example, the 2.5th percentile and the 97.5th percentile from the chi-squared distribution, and looking at the probability that this chi-squared random variable n-1 s squared over sigma squared is between those two quantiles, well, that has to be 1 minus alpha, just by the definition of those being the 2.5th and 97.5th quantiles of the chi-squared distribution. So this equality holds the equality that 1 minus alpha equals this probability. So this statistic, n minus 1 s squared over sigma squared, is our pivot. Let's solve for the parameter that we're interested in, sigma squared. And you do that, keep track of your inequalities, being sure to flip them if you invert everything and that sort of thing. And you wind up with the following probability statement. There's a 1 minus alpha probability that the random interval n minus 1 s squared divided by the upper quantile and n minus 1 s squared divided by the lower quantile contains sigma squared. So we call this interval, the n minus 1 s squared divided by the two quantiles, we call that interval a confidence interval for sigma squared. And because the probability that the random interval contains the parameter it's estimating is 1 minus alpha, we call it, say, a 100 times 1 minus alpha % confidence interval. So as an example, alpha might be 0.05, and so you then wind up with a 95% confidence interval for the parameter sigma squared. Now we should talk a little bit about what this confidence interval means. It's the interval that's random. In the paradigm that we're sort of thinking about here, the interval is random, and the parameter, sigma squared, is fixed. So when you actually collect data and you form this confidence interval, it either contains sigma squared, which you don't know, or not. There's no probability with that statement anymore. It's either 1 or 0. It either contains sigma squared or not. So what's the actual interpretation of a confidence interval? Well, if you take an intro stat class, they make a lot of hay out of this point, and they basically say, okay, the confidence interval is a procedure that if you were to repeatedly do the experiment and form confidence intervals, 95% of the confidence intervals, say if you're creating 95% confidence intervals, 95% of the confidence intervals would contain the parameter that you're interested in. And you could, as an example, do this in R. You could generate normal data. You could, from a normal, let's say mu is 0, from a normal 0 sigma squared distribution, you could formulate this confidence interval from the sample variance. You could check whether or not that interval contained the sigma squared that you used for simulation. And then you could repeat that process over and over and over again. And you will find that about 95% of the intervals that you get, if you construct 95% confidence intervals, will contain the sigma squared that you used for simulation. And that's the logic behind confidence intervals. And they're a little notoriously hard to interpret if you go for this sort of hardball interpretation. They're notoriously hard to interpret. Kind of a much weaker interpretation of the confidence interval that's a little less specific is you get two numbers out, and these two numbers are an interval estimate of the parameter that you want to estimate, but the interval estimate incorporates uncertainty. So let's go through a couple of comments about this interval. So one thing is this interval is not terribly robust to departures from normality. So if your data is not normal, then this confidence interval tends to not be that great. Also, if you want a confidence interval for the standard deviation instead of the confidence interval for the variance, you can just square root the endpoints of the interval. The probability statement 1 minus alpha equal to the probability that the random interval contains sigma squared, well, you can still say that that's 1 minus alpha is equal to the probability that the square root of the endpoints of the interval contains sigma, and you haven't mathematically changed anything. So if you want an interval for sigma, you just square root the endpoints. So you might be wondering, okay, well, if this is heavily requires normality, do we have any other solutions other than this interval if we want a confidence interval for the variance? And it turns out the answer is yes, and there's several ways, but bootstrapping is kind of the way that I prefer. But we're not going to talk about bootstrapping in today's lecture. So today we're only going to talk about this confidence interval when you happen to be willing to stomach the assumption that your data is exactly Gaussian and you are willing to live with the consequence that the interval that you obtain is not going to be terribly robust to departures from that assumption. So the other thing I wanted to mention, it's kind of a nifty little point, is suppose you wanted to create a likelihood for sigma. And in this case, the underlying data is Gaussian with mean mu and variance sigma squared. So it's hard because you have two parameters. The likelihood is a bivariate function, right? It has mu on one axis, sigma on the other axis, and then the likelihood on the vertical axis. So there's a little trick you can use to create, I guess, what I would call marginal likelihood for sigma squared. It turns out, and we're not going to cover the mathematics behind this, but that if you don't divide by sigma squared, n minus 1 s squared, and then don't divide by sigma squared, well, first of all, that can't be chi squared. Let me just logic through that real quick. That can't be chi squared because the chi squared density doesn't have any units, right? So s squared has whatever units the original data has, say it's in inches, it has inches squared units. So you haven't divided by anything that's in inches squared. So n minus 1 s squared has inches squared units. And so it can't follow a distribution that's unitless like the chi-squared distribution. That's one of the reasons why you have to remember to divide by sigma squared to get the chi-squared distribution, is you get rid of the units. Well, let's suppose we don't divide by sigma squared. Then you wind up with a gamma, and a so-called gamma distribution. And the gamma is indexed by two parameters, its shape parameter and its scale parameter. In this case, the shape parameter is n minus 1 over 2, and the scale parameter is 2 sigma squared. And either way, what you have is data. You have a single number, n minus 1 s squared. And if you're willing to assume the data points that comprise that number are Gaussian, then you can take the gamma density and plug in the data and view it as a function of the parameters and plot a likelihood function. So I'll go through an example of doing this. So in our organo-lead manufacturing workers example that we looked at before, there was an average total brain volume of 1,150 cubic centimeters with a standard deviation of 105.977. And let's assume normality of the underlying measurements, which is not the case, but let's do it. And let's calculate a confidence interval for the population of variation in total brain volume. I give the R code here. So I gave the standard deviation. So our variance is 105.106 squared. Our n in this case is 513. Confidence interval, we want a 95% confidence interval, so our alpha is 0.05. The quantiles that we want, we can just use the q chi sq function to grab those quantiles. This function right here just grabs the two quantiles. And then our interval is just n minus 1 s squared, the s squared divided by the quantiles. And then this puts it out from bigger to smaller. I want it from smaller to bigger, so I use the RAV function to reverse it. I think if I had just input my quantiles in the reverse direction, I would have been okay, too. And then here, just take the square root of that interval for an interval for the standard deviation, and we get the interval is about 100 to 113. So this interval, 100 to 113, is created in a way such that if the assumptions of the interval are correct, namely that the underlying data are IID, normal with a fixed variance sigma squared and a fixed mean mu, then the procedure, if repeated over and over again, 95% of the intervals that we obtain would be intervals containing the true standard deviation that we're trying to estimate. Let's actually plot the likelihood as well using this kind of likelihood trick that I gave. So sigma vals is the sequence that I want to plot. And actually, I don't have to guess this because I just created this confidence interval on the previous page that went from 100 to 113. So let's, for good measure, go from 90 to 120, and I want to plot 1,000 points. In R, you kind of have to actually be pretty specific about the range that you want to plot and how many points you want going into your plot. And then I just give you the code here for evaluating the gamma likelihood. It says basically plug in the data, n minus 1 s squared, right? And remember the likelihood views that as fixed. The shape doesn't involve anything other than things we know, n minus 1 over 2. And then the scale is the part that varies, 2 sigma squared. And here we're going to evaluate it over all the sigma vals that I assigned in the previous line. So this will evaluate that likelihood over 1,000 points and return a vector of length 1,000. I want to normalize my likelihood, and I'll just kind of, mostly approximately do that by taking this vector and dividing by its maximum value. And then I'll plot it. Type equals L means plot it as a line instead of as a bunch of points. And then these two lines commands adds the 1/8 and 1/16 reference lines. And then on the next page, you actually see the marginal likelihood for sigma. That's a whirlwind tour of creating confidence intervals and likelihood plots for variances when you're willing to assume your data is exactly Gaussian. I hesitate to say this, but kind of those slides aren't exactly terribly useful material. You won't find a lot of people plotting marginal likelihoods for sigma. I just gave it to you because it's kind of a nifty little result. And to be honest, the Gaussian confidence interval for variances, you don't see them as much. People just would tend to do bootstrapping these days instead, or some other more robust technique. So this material, it's neat, and it's the primary thing to do was actually introduce the chi-squared distribution. So next, we're going to talk about something that's incredibly useful, probably one of the single most used distributions and techniques in all of statistics. Okay, welcome back, troops. We're going to start talking about student, or as I like to say, Gosset's t-distribution. So the reason I call it Gosset's t-distribution is it's usually called student's t-distribution because Gosset published under the pseudonym student in 1908. So it was actually Gosset's distribution. He laid the groundwork for the actual distribution, and then I believe Fisher actually proved the mathematics, some of the finer scale mathematics. But I wanted to talk a minute about Gosset because he's a pretty interesting character in the annals of statistics. So Gosset was a researcher, and he worked at the Guinness Brewery in Ireland. And when he created the t-distribution, he was actually working for Guinness. And at the time, he had actually several really brilliant researchers working for him, and he wouldn't let them publish under their real names. So that's how Gosset wound up publishing under a pseudonym and made this sort of landmark discovery as a researcher. It's interesting. So the reason he came up with this distribution is because for him, the central limit theorem just was simply not rich enough to describe the problems he was looking at. So he was working with these small batches in the science of brew making, and it wasn't adequate to assume that things were heading to infinity. So he came up with this distribution, and we're all the more fortunate for it. One thing I really like about Gosset is whenever you read about him, he was apparently a tremendously nice guy, extremely humble. He made several major discoveries in statistics. He came up with one of the first uses of the Poisson distribution. And then he also, in the Guinness company, he rose up pretty high. He was a head brewmaster at I think it's London Brewery by the time he had retired. So anyway, he's a really interesting character. And if you get a chance, you should read about him. At any rate, so he came up with this wonderful distribution called, as far as I'd like it to be called, Gosset's t-distribution. And the t-distribution is really kind of used when you have smaller sample sizes. It assumes your data is Gaussian, but it tends to work even if your data is non-Gaussian. And so the t-distribution, it has degrees of freedom. It's indexed by something called degrees of freedom. And the t-distribution, which looks like a normal distribution where someone kind of squashed it down at its tip and all the extra mass went out into its tails, well, it looks more and more like a standard normal as the degrees of freedom get larger and larger. So how do you get a t-distribution? Say you wanted to simulate it on a computer. You would take a standard normal, say z here, and you would divide it by an independent chi-squared divided by its degrees of freedom. So where z and chi-squared here are independent standard normal and chi-squared random variables, that's how you wind up with a t-distribution. So how's this useful? On the next slide, we'll look at how we apply this. Well, let's suppose x1 to xn are IID normal mu sigma squared. Then x bar minus mu divided by sigma over square root n is, of course, standard normal, right? Because linear combinations of normal random variables are themselves normal. So in this case, x bar is normal. And because they're IID, we know exactly what the standard deviation of x bar is. It's sigma over square root n, and we know that its mean is mu. And so when we shift and scale our non-standard normal by mu and divide it by its standard deviation, sigma over square root n, we get a standard normal. Hopefully this should not be news to you at this point in the class. And then we also know from earlier on in today's lecture that n minus 1 s squared over sigma squared is chi-squared with n minus 1 degrees of freedom. So if we take n minus 1 s squared over sigma squared and divide it by an additional n minus 1 and square root the whole thing, we get s over sigma, and we've taken a chi-squared and divided it by its degrees of freedom. So s over sigma is the square root of a chi-squared divided by its degrees of freedom. Therefore, if we take x bar minus mu divided by sigma over square root n, and then divide the whole thing by s over sigma, which if we do the arithmetic works out to be x bar minus mu divided by s over square root n, we wind up with a standard normal divided by a square root of a chi-squared divided by its degrees of freedom. Now, there's one small thing that we're kind of fudging over. We haven't showed that the x bar and s are independent, right? They're from the same data, so does it seem obvious that they're independent? They are. It's just not immediately clear, and let's sweep that under the rug. So forget about that for the time being. Take my word for it. X bar and s are independent, so this exactly has Gosset's t distribution with n minus 1 degrees of freedom. And notice what it basically accomplishes. So we saw previously in constructing confidence intervals that x bar minus mu divided by sigma over square root n, that's a nice kind of pivotal statistic to work with. It's useful for generating confidence intervals. We'll see that it's useful for doing hypothesis tests. And all we've done is replace sigma by s. And it's basically saying that we can take the unknown population variance and replace it with the known sample variance, and we get a statistic whose distribution we know, okay? And by the way, this statistic, x bar minus mu s over square root n, it also limits to a standard normal as n goes to infinity, which, of course, the Gosset's t distribution is the degrees of freedom goes to infinity. If you look at it, if you plot it, it looks more and more like a normal distribution as n goes to infinity. So we haven't violated the central limit theorem or anything like that in the process of doing this stuff. So let's actually use this distribution to create a confidence interval. It's a statistic who, under the assumption of normality of the underlying data, does not depend on the parameter mu that we're interested in, and therefore we can use it to create a confidence interval for mu. So let's let t df alpha be the alphth quantile of the t distribution. So t n minus 1, 1 minus alpha over 2 is, say, the upper quantile from the relevant t distribution, and t n minus 1 alpha over 2 is the lower quantile from the relevant t distribution. And so this probability statement here, 1 minus alpha, is equal to the probability that this statistic lies between those two confidence intervals is then, of course, true, right? So the probability that this t random variable lies between the alpha over 2 lower quantile and the 1 minus alpha over 2 upper quantile is exactly 1 minus alpha. Oh, and I should note here, by the way, because the t distribution is symmetric, the alpha over 2th lower quantile is equal to the negative of the 1 minus alpha over 2 upper quantile. This is because the t distribution is symmetric about 0. So that's why here, instead of writing alpha over 2, I wrote negative t n minus 1, 1 minus alpha over 2. And you'll see why I do that in a second. So anyway, this probability statement applies here. So we can just rearrange terms and keep track of flipping our inequalities around when we multiply by a negative sign. And we get that x bar minus a t quantile times the standard error is less than mu, and x bar plus a t quantile times the standard error is bigger than the mu. That random interval contains mu with probability 1 minus alpha. But if you look at the form of this interval when I wrote it out this way, that happens to be x bar plus and minus the upper quantile from the t distribution times the standard error. And that's why I took only the upper quantile. That way we can write it as plus minus. Okay, so that's how we wind up with these intervals. Estimate plus or minus quantile times standard error. And that's where it comes from. This interval assumes that the data are IID normal, though it's very robust to this assumption. Whenever the data is kind of roughly symmetric and mound-shaped, the t confidence interval works amazingly well. And if you want, if you have paired observations, people before and after a treatment, for example, you can subtract them and then create a t confidence interval on the difference. So often paired observations are analyzed using this exact confidence interval technique by taking differences. And often differences tend to be much more Gaussian looking. They tend to be nice and symmetric about 0. And then for large degrees of freedom, the t quantiles become the same as the standard normal quantiles. And so this interval just converges to the same interval that you get as the CLT. Some more notes. For skewed distributions, the kind of spirit of the t-interval assumptions are violated. You could probably show that it still works kind of okay, and the reason is because those quantiles, the t n minus 1, 1 minus alpha over 2, the quantiles are so far out there. You know, the t-distribution is a very heavy-tailed distribution that shoves those quantiles way out there. That makes the interval a lot wider, and then it tends to work kind of conservatively in a broad variety of settings. But for skewed distributions, you're kind of violating the spirit of the t-interval, and you're often better off, trying some things like taking a natural log of your data if it's positive to get it to be more Gaussian looking before you do a t-confidence interval. And we'll spend an entire lecture on the consequences of logging data, so you can wait for that. But, I would just say for skewed distribution, it kind of violates the intent of the t-interval, so maybe think of things like doing logs to consider it. And also, I would say for skewed distributions, maybe it doesn't make as much sense to center to the interval around its mean in the way that we're doing with this t-interval. We're centering it right around the mean. And then the other thing, for discrete data, like binary data, again, you could probably, I bet you could do simulation studies and show that the t-interval, actually probably works okay for discrete data like binary data. But, we have lots of techniques for binary data that make direct use of the binary data. And you're better off for those using, for example, things based on chi-squareds or exact binomial intervals and that sort of thing, because, you're so far from kind of the spirit and intent of the t-interval that it's not worth using. Regardless, the t-interval is an incredibly handy tool. And I'm sure actually in some of these cases it probably works fine, but you're so far from the kind of assumptions at that point that you're better off using all these other techniques that have been developed for these other cases. That's enough discussion about the t-confidence interval. Let's go through an example. So maybe take a break, go have a Guinness, and we'll be back in a second. Okay, so welcome back. So we're going to talk about Guinness's original data, which involves sleep data. So try not to fall asleep while we're talking about it. So Gosset's original data appeared in this journal called Biometrica, with a K. And Biometrica, interestingly enough, was founded by a person called Francis Galton. So Gosset was an interesting character. If you really want to read up on another, absolutely brilliant, interesting character, read up on Gosset. He was Charles Darwin's cousin. He invented the term and the concept regression. He, invented the term and the concept correlation. And he invented lots of other things, some good, some bad. And he was just a generally rather interesting character. So, at any rate, Biometrica was founded by Francis Galton, and that is where Gosset's original paper appeared, and that's where this sleep data occurred. So, at any rate, the sleep data shows the increase in hours slept for 10 patients on 2 sleeping drugs. So, R treats the data as 2 groups rather than paired, and I have to admit, I haven't taken the time to go through and figure out exactly why there's a discrepancy between when you read Gosset's Biometrica paper, which treats the data as paired, and R treats it as 2 groups. And anyway, I haven't gone through the details, so I'm going to treat it exactly like Gosset's data. So here's what it looks like as Gosset's data. So we have patient 1, 2, up to 10. We have the 2 drugs and the difference. And here's the code I used to get it that way. So the mean would be the mean of the difference, and here I just put in a comment the value that it comes out to be. It turns out to be 1.67. And this is, remember, everything's normalized relative to 10 hours. And then the standard deviation was the standard deviation of the collection of differences is 1.13, and we had 10 subjects. So our confidence interval is the mean plus or minus the t quantile at 0.975 if we want a 95% confidence interval, because remember we put 2.5% in either tail, times the standard error, which is s divided by square root n. And this will give you our confidence interval manually, but if you want to go the easier way, R actually has a function, of course, to do the t confidence intervals because it's one of the most popular statistical procedures. So if you do t dot test, and here difference is the name of the vector that contains the differences. And then this $ sign here grabs the relevant output. So in this case, I want the confidence interval. So it's $conf.int. If you omitted the $, when you hit return, it would give you lots of information, including the confidence interval. Here, it just returns exactly the confidence interval. And you get 0.7 to 2.5, basically. We've talked a lot about likelihoods, so I wanted to talk about how you can use the t-distribution to create a likelihood for not mu. So remember, we're in this kind of hard setting where we have a data that have two parameters, mu and sigma. You know, the likelihood inherently is a two-dimensional object. And we showed, oh, well, you can get a trick and figure out how to get a likelihood for sigma. And here I'm going to say, well, here you can do another trick and get another likelihood for a single parameter, but the single parameter is a function of the two parameters. So in this, the single parameter is mu divided by sigma, which is actually quite an important parameter. Mu divided by sigma is the mean in standard deviation units. So it's a unit-free quantity, and it's often called the effect size. And this is a nifty little trick to create a likelihood for the effect size. So if x is normal mu sigma squared, and then this chi-squared random variable is a chi-squared random variable with df degrees of freedom, then if you take x divided by sigma and divide it by the square root of a chi-squared divided by its degrees of freedom, then notice we forgot to subtract off mu in the top. So x over sigma still has a mean. In this case, its mean is specifically mu over sigma. So we've not taken a standard normal and divided by an independent square root of an independent chi-squared divided by its degrees of freedom. We took a non-standard normal and divided by a square root of an independent chi-squared divided by its degrees of freedom. Well, so it can't work out to be a t random variable because we haven't satisfied the definition of a t random variable. So it's what's called a non-central t random variable. And in the specific case when mu is 0, we wind up with a t random variable. And this non-central t random variable also has degrees of freedom, but then it has a second parameter called the non-centrality parameter. In this case, the non-centrality parameter is mu over sigma. So just to put this in context, x bar is normal mu with variance sigma squared over n minus 1 s squared over sigma squared is a chi-squared with n minus 1 over n minus 1 degrees of freedom. So square root n x bar divided by s works out to be a non-central t with non-centrality parameter square root n mu divided by sigma. At any rate, we can use this fact to create a likelihood for mu over sigma. The effect's basically what is called the effect size. And we can plot a one-dimensional likelihood without having to do any further tricks. And then after this, I'll talk about how you can do a trick to avoid all these little, figuring out a likelihood for the effect size and figuring out a likelihood for the variance are sort of, you'd have to kind of take a math stat class to figure those out. What we'll talk about next in profile likelihood is a quick way to always generate a likelihood in any setting in a fairly automatic way. So anyway, here's how you would create the interval. So here our t statistic is square root n times the mean divided by s, just using the code from the sleep data. The effect size values that we want to plot is, let's say we go from 0 to 1 and our length is 1,000. Our likelihood values are then the t density. In this case, r's dt function, t density function, has an argument ncp, which stands for non-centrality parameter. So here we have our t density. We plug in our t statistic. Our degrees of freedom are n minus 1. And then we loop over all of our non-centrality effect sizes. And that creates a collection of likelihood values. And then we want our likelihood values to be peaked at 1. So instead of figuring out what the exact maximum likelihood is, let's just divide by the maximum when we grid searched over 1,000 points. And let's plot our effect size values by our likelihood values. Let's make sure it's aligned by doing type equals L. And let's draw lines at 1/8 and 1/16. And we wind up with this plot. So this plot is a likelihood not for mu, but for mu divided by sigma. And it has all of the same interpretations of any likelihood. Higher values indicate better supportive values of mu over sigma. Lower values of likelihood indicate worse values. And where the two lines intersect the likelihood represent intervals for the effect size. So that's maybe enough about the effect size. And that's a fairly specific thing. That's not something you'll see in many, say, introductory stats textbooks. I just thought I'd give it because it's kind of neat. Next, we'll talk about a way for creating a likelihood when you have a multivariate likelihood, creating a univariate likelihood to look at. So welcome back. The final thing we're going to do in today's lecture is to talk about the profile likelihood, which is a method for creating univariate likelihoods from multivariate likelihoods. And in this case, we're going to look at the bivariate normal distribution, which has two parameters, mu and sigma. And we're going to figure out how to get likelihoods for mu alone, and you could equivalently do it to get likelihoods for sigma alone. And here's the idea. The multivariate likelihood is a bivariate surface. It has mu on one axis, sigma on another axis, and this surface above it. And to obtain a likelihood for mu, profiling is basically like, let's imagine we took a lamp and shined it along the sigma direction and looked at the shadow that the likelihood placed on the plane defined by the mu direction. And that's exactly what it gives. So its name is exactly indicative of the technique. And then now we'll just go through how do you actually execute the mathematics to do that. So in other words, we want to shine a light on this bivariate likelihood, and we want to get the function that you obtain onto, say, the wall where the shadow occurs. Okay, so let's pick a particular value of mu naught, and we want to know what's the value of this curve in the shadow at mu naught. Well, basically, the light will go through all values above the likelihood and will get stopped anywhere on the likelihood and up until the maximum value. And so what we basically do is we maximize the joint likelihood for sigma with mu fixed at mu naught. And then this process is repeated for lots of values at mu naught. So let's actually go through it. So the joint likelihood with mu fixed at mu naught is just the Gaussian density, and then we have independent data, so we take a product out front. So it's sigma squared to the minus 1/2, e to the minus xi minus, and we're fixing mu naught squared divided by 2 sigma squared. And collect all the terms and you get the next line. With mu naught fixed, then the maximum likelihood estimator for sigma squared, and you can go through this, log the likelihood, take derivatives, solve for sigma squared. So maybe just so you don't accidentally take the derivative with respect to sigma, replace sigma squared, say, by theta, so that you remember that you're fixing sigma squared as the parameter, not sigma as the parameter. If you accidentally take derivatives with respect to sigma, you'll get the square root of this answer, of course. So then you wind up with a summation I equals 1 to n, xi minus mu naught squared divided by n. That's actually a nice result, right? If you fix mu at a particular value, then your MLE for sigma squared is the sample variance, but instead of plugging in the sample mean and subtracting deviations around the sample mean, you're subtracting deviations around that specific value of the mean. So it's a nice little result. So at any rate, with mu naught fixed, the maximum likelihood estimator for sigma squared is this generalization of the variance right there. So that's the peak of our likelihood, all right? That's the point where the light switches from being able to not go through the likelihood to the point right above it where the light is actually, passes over the likelihood. And that's that point. That's that point that gets shadowed onto the wall at mu naught. And so we want to plug this back into the likelihood, and we get this function right here. Summation xi minus mu naught squared over n raised to the minus n over 2 power, and then e to the negative n over 2. And this e to the negative n over 2 is irrelevant because it doesn't involve mu naught. So that's for one mu naught, and if we did that for every mu naught, we would get a function. And so here's our profile likelihood is this function, summation xi minus mu squared raised to the negative n over 2. That function is our profile likelihood. And then again, this function's clearly maximized at mu equal x bar. You can, of course, solve it. But in general, one nice property of the profile likelihood is that the maximizer of the profile likelihood, the maximum profile likelihood estimate, is also your MLE for the parameter. So in this case, the maximum of the profile likelihood for mu is going to be x bar, the same as the maximum likelihood for the complete value. So if we wanted to divide this by its peak value, we would simply divide it by the same thing, and with instead of mu there, plug x bar in, and then that would normalize this function so it tops out at 1. So let's actually go through the R code to generate this function, our mu for the sleep data. So our mu vals, we're going to go from, say, 0 to 3 and do 1,000 of them. So we'll plot a function of 1,000 mu naught values. Our likelihood values, and then so it would just be this sum, xi minus mu squared sum raised to the minus n over 2 power. So that's this term right here, raised to the negative n over 2 power. But I want it to be maxed out at 1. So normally I create the likelihood and then divide by its maximum value. But in this case, I know exactly what the exact maximum value is. It's when you replace mu by the mean. So instead I divide it by the mean right here. And this sapply is just a loop. It says loop over mu values and do this function. And then I'll plot them and connect them together with type equals L. And then I'll put the likelihood values above 1/8 and above 1/16, and then I get this plot. So that is my profile likelihood for mu. That is the function that I get if I take the bivariate likelihood for mu and sigma, place a light along the direction of the sigma axis, and look at the shadow on the wall. This is the outline of that shadow, and that's called the profile likelihood. And there's many theoretical properties of the profile likelihood, but most importantly, you can kind of treat them as if they were a standard univariate likelihood. So you would treat this just like a regular likelihood for mu. The higher values are better supported. The peak is where the maximum likelihood estimate occurs, and you could draw horizontal lines to get likelihood-based intervals for mu. Well, that's the end of today's lecture. We gave you many ways to create confidence intervals. We gave you methods for creating T confidence intervals. We gave you a method for creating a confidence interval for a variance, maybe not the most useful one, but we did it. We also showed you lots of really neat, kind of well-known among statistics circles, but not generally well-known techniques for generating likelihoods when you have Gaussian data. And so all of these techniques you could use in practice if you have data and you're willing to assume that it's Gaussian. All of the techniques would apply. The specific technique of the T confidence interval is a very robust interval. As long as your data looks roughly mound-shaped, then you're going to be okay. The last thing I always mention is a question I always get about the T confidence interval is basically the T confidence interval and the standard normal confidence interval look the same except with the T quantile replaced by a standard normal quantile. And people always ask me, at what point do I switch, what sample size do I switch between a T confidence interval and a standard normal confidence interval? But the point is that the T confidence interval limits to the standard normal confidence interval. So my answer to that is just always do a T confidence interval. Just never do a standard normal confidence interval. And then you don't even have to worry about it, because if your sample size is big enough, that T quantile looks just like a normal quantile anyway. So hopefully that answers that question. And I look forward to seeing you next time, where we'll expand on confidence intervals for more general settings where we have multiple groups.